Welcome to today's presentation entitled Introduction to Digital Signal Processing. My name is Dr. Jim Batty, and I work at the NASA Langley Research Center in Hampton, Virginia. I'm a member of the NASA Engineering and Safety Center Flight Mechanics Technical Discipline Team. This presentation is part 4 of a 4-part discussion about digital signal processing and is sponsored by the NESC as part of its educational outreach program called the NESC Academy Online, which is a collection of video and audio presentations in a number of technical disciplines of interest to the NASA community. Today's presentation is entitled Typical GNC Applications. As an overview of the 3 previous parts of this 4-part presentation that were provided earlier, Part 1, entitled Mathematical Concepts, laid the framework for digital signal processing by defining the mathematical techniques that are used in its construction. We defined the definitions of Fourier transforms and the convolution operator. We defined discrete Fourier transforms and the fast Fourier transform, or FFT, implementation that provides more efficient calculation of the discrete Fourier transforms themselves. In Part 2 of this 4-part presentation, Power Spectral Density Basics, we covered the definition of power spectral density, or PSD, and how it's used to estimate spectral characteristics of waveforms. We concluded Part 2 with a demonstration of the PSD technique for a sequence that was devised and constructed of several sinusoids and a constant bias part and a random component, and then we showed how you can use the PSD processes to extract the information in that waveform and characterize its frequency content. In Part 3 of this series, entitled Implementing Discrete Filters, we showed how you actually go about using discrete filters by converting from continuous Laplace domain filters to their Z-domain or discrete filter counterparts using Tustin's rule, or also known as the bilinear transformation. And we showed examples of how you would build recursive filters that would implement those discrete filters. In this 4th and final part of this presentation, which is entitled Typical GNC Applications, we'll discuss several important concepts that are useful and necessary in actually using the discrete filters for a typical application, as you might find in a digital controller in a flight vehicle. We'll start off by discussing normalized frequency and what that means and how that's related to the discussions we've had previously in the first 3 parts regarding normalized frequency. We'll also discuss methods that we can use to verify transfer function magnitude and phase of discrete filters using discrete Fourier transform. And that's important, as we mentioned in the previous discussion, to make sure you understand how filter coefficients were computed, assuming you were, for instance, given filter coefficients for some discrete filter and asked to implement them. So one of the first things you should do is try to verify that you understand what you're getting and that you're using them correctly. So I'll show an example of how you can compute the Bodie plot, or the magnitude and phase versus frequency of a discrete filter, having been given the filter coefficients, the numerator denominator coefficients of that discrete filter. Then we'll conclude today's presentation and the final presentation in this series with an example of how one might use the discrete filter to implement a notch filter, actually a notch low pass filter, where we'll build a signal that has some low frequency component, a component that's within the notch, the range of the notch filter, and a component that's above the low pass, and we'll demonstrate that that filter then removes those higher frequency components and retains the lower frequency component. As stated, one of the first things we'll talk about today to kind of set the framework again for some of the concepts that are somewhat confusing about discrete or digital filters, and that's normalized frequency. What do we mean by it? You may recall in earlier parts of this discussion, normalized frequency is the actual frequency divided by the sample frequency, and it typically runs for real discrete sequences. It runs from 0 to 0.5, where 0.5 represents the Nyquist frequency, as it's called, which is half the sample frequency. Now in the Laplace domain, or the S domain, or for continuous filters, typically we define the filter response in terms of a natural frequency which is also can be known as a lot of times as a corner frequency, and it's usually specified in radians per second. And kind of the convention used for that, if the filter is defined in radians per second, they usually use the Greek symbol omega, or sometimes omega n for a lag frequency and omega L for a lead frequency, to note that filter frequency. Sometimes, however, it might be defined in hertz or cycles per second. And again, the convention, not always followed, but the convention is a lot of times lowercase f is used for a frequency that's in hertz, or sometimes f sub n is used to denote a low-pass filter frequency. Again, those are not universal definitions or conventions, but many times they're used. When Laplace domain filters are converted to discrete filters, as you might recall from part 3 of this presentation, using Tustin's rule or the bilinear transformation, you'll end up with terms in the discrete filter coefficients, terms like omega times t over 2. Well, the quantity omega t is very important in discrete filters because the filter is entirely described by by its normalized frequency, which I'll show is related to the parameters omega t that we see when we convert filters from the Laplace domain to the discrete domain, or Z domain. And the normalized frequency, as I said, is the natural frequency of the filter in hertz divided by the update frequency in hertz of the discrete filter. And that's just the rate at which it's called in hertz. So if we define like Fs as the sample frequency in hertz, it's also related to the sample period, capital T, is just Fs is 1 over T. Now, also, since T is 1 over F of S, then the term that we talked about above, omega times T over 2, can be written in terms of its frequency in hertz as 2 pi f, and then T can be represented as 1 over F sub S. So then omega T over 2 is the same as 2 pi times F divided by Fs divided by 2. That simplifies to pi times F over F sub S. So basically, the quantity Wt over 2 that we see when we convert filters from the continuous domain to the discrete or Z domain, they can be entirely defined by the normalized frequency multiplied by pi. Again, continuing this discussion about normalized frequencies, as we said earlier, for entirely real sequences, the range of normalized frequencies is 0 to 1. Now, for complex sequences, the range is plus or minus a half, where the negative portions of the frequency are caused by the complex parts of the sequence being evaluated. Now, for normal applications, for what we would use like in real-world flight mechanics types issues or guidance and control issues, the sequences that we'd be operating with are entirely real. So our normalized frequencies generally would be from 0 to plus 0.5. Now again, the plus 0.5 or the 0.5 represents the Nyquist frequency, which is half the sample frequency. And an important thing to recall or to make note of is a discrete filter cannot implement frequencies above the Nyquist frequency. That's just a basic limitation in how the sampling works. And we discussed this in a lot of different aspects in parts 1, 2, and 3 of this presentation. You might recall in part 1, the concluding part of that presentation discussed Shannon's sampling theorem and data aliasing and the ramifications of the Nyquist frequency and how sampling affects your quality of the signal you're sampling. And again, the final bullet here is to convert this normalized frequency that you might get computed by a discrete Fourier transform or fast Fourier transform into a quote real frequency, which has units of hertz or radians per second. You would just multiply the normalized frequency by the sample frequency f sub s to convert it to hertz, or 2 pi times the sample frequency if you wanted the output frequency to be in radians per second. I'll discuss briefly here just a technique which is not often used, but sometimes it is, referred to as frequency warping. As just described earlier, discrete filter implementations are limited to frequencies less than the Nyquist frequency, which is again half the sample frequency. But if you have a filter that approaches that limit, the approximations that are used in Tustin's rule might cause a discrete filter's frequency response to differ from its continuous filter counterpart, which is caused by what's called frequency warping. And you might remember the transformation from the Laplace domain to the Z domain used an approximation for log of Z. And that approximation is what we're running into here when you have filters that are up close to the Nyquist frequency, or have components in their filter up near the Nyquist frequency. You can counteract this by a technique called pre-warping the filter's corner frequencies. And in this technique, the corner frequency, let's just call it omega n, can be pre-warped to something called omega d using the following technique. If we just define omega d as 2 over the sample period t times the tangent of the unwarped or natural frequency omega n times t over 2, and then you can simplify that in terms of the normalized frequency as described on the earlier chart. So basically you can then pre-warp omega n into the frequency omega d. Now how would you use that? Well, you would just take that omega d that we computed on the previous slide and just use it in place of omega n. So you may recall again the filter coefficients that we would get for the discrete filter would have terms like omega n t over 2. Well, you would just replace the omega n with omega d. And what will happen is the pre-warping of this corner frequency will cause the discrete filter to have the exact gain and phase as a continuous filter at that desired corner frequency. But a couple of things to note here is, the gain and phase at other points will still be different than the continuous filter, and so the overall match, if you will, of the gain and phase of that discrete filter or digital filter compared to its continuous counterpart may be actually worse than it was before you pre-warped it. So why would you do that? Go to the trouble of pre-warping your filter coefficients. The reason is if you had a filter that's that has to be defined at a specific filter, such as like say a notch filter, where if you have any mismatch of the frequency response, you might not actually cut out the frequencies that you're actually intending to. So in that case, you might want to pre-warp your filter to line up the magnitude or the attenuation of the filter and the phase at the proper frequencies. So I'll just show a brief example here of a first order lag transfer function with a corner frequency of 15 Hertz that's got a sample time of 50 Hertz. And we'll show on the next slide a Batty plot of what you get when you do the pre-warping versus not pre-warping. So what's shown here is a Batty plot of magnitude versus frequency and on the top, and phase versus frequency on the bottom. The three curves that are shown there, the red curve is a discrete implementation of the filter without pre-warping. The blue line is a continuous filter that presumably you're attempting to replicate with this discrete filter. And the black line is a discrete filter where we've pre-warped the corner frequency omega n by the technique showed 2 slides ago. So again, just to recap the constants in here, the natural frequency of the filter is 15 Hertz. So omega n, as we described a couple of charts earlier, is 2 pi times f sub n, or 94.248 radians per second. If you follow the technique that was provided 2 slides ago for how to compute the pre-warped frequency called omega d, you'd find out it comes out to a value 137.638. So basically we would go back and recompute the discrete filter coefficients as described in part 3 of this presentation using omega d of 137.638 radians per second rather than the normal corner frequency of 94.248. If you do that, you'll note what's shown by the note there inside the Batty plot. Now you'll notice the black line, which is the discrete filter with pre-warping, matches both the gain and phase exactly at 15 Hertz. In other words, the black line crosses the blue line right at 15 Hertz for both the gain and phase, where the red line, which is the discrete filter without pre-warping, both the gain and the phase are significantly, I don't know if it's significant or not, but it depends on your application, but they are different than what they are when you've pre-warped it. And again, for this particular filter, you might say, well, the black line is no better of a match than the red line. But if it's critical that you match the gain and phase characteristics at 15 Hertz, then this is a technique that can be used to ensure that. As mentioned earlier, one of the things you can do with, or one of the techniques that you might use to verify the transfer function frequency response of a discrete filter is what we're going to talk about here. And why would you want to do that? As I attempted to provide some guidance in part 3 of this presentation, that it's very, very important to make sure you understand what assumptions went into computing the discrete filter coefficients for a digital filter, and particularly the denominator coefficients. There's a couple of conventions that are used there. One is you assume there's a leading value of 1, assume they've been computed such that the denominator has a leading coefficient of 1, which is usually not even provided to you because that's assumed. And then the other assumption is the remaining coefficients of the denominator all are defined with a leading -1 on them. And if that's not the case, that you will not get the response out of the discrete filter that you expected, because there'd be a mismatch between how you're interpreting them and how the person who computed them is interpreting them. So I strongly recommend, if you're building a digital filter and you didn't build the coefficients yourself, to go through this process to compute the transfer function's frequency response and verify that you understand what you have before you proceed to the next step of the implementation. So how you do that is you can compute the impulse response, which is also called the filter kernel of the discrete filter, by passing, let's call it an n-sample impulse response through the filter. And all that means is you're going to build a signal of n samples where the first value, sample number 1, has a value of 0. All other samples have a value of 0. And that's what's meant by an impulse response. So you can take a recursive filter, as we've shown in part 3 of this presentation. You can build a function that performs a filter recursion given the numerator polynomial A and the denominator polynomial B. You can calculate it as shown here by the recursive filter. Just the impulse response of the filter X would be the recursive filter where you provide it the impulse as the first parameter, and then the numerator denominator polynomials as the second. And again, this was described in part 3 of this topic. And also the caveat there in bold, make sure you understand how those denominator polynomial coefficients are defined. So then once you've done that, you have X contains the impulse response of that discrete filter. So now you can compute the frequency response of that impulse response by computing its discrete Fourier transform. And there's 2 ways you can do that, at least 2 ways. You can do what I referred to in part 1 of this presentation as brute force. There's one of the basic definitions, the kind of initial definitions of the discrete Fourier transforms is a summation. And it's actually, as you recall, a summation over n squared. It would take n squared calculations to do it, where n is the size of the sequence x that you're trying to compute the discrete Fourier transform for. So the first example here shown here would be just computing the magnitude and phase by what I call the brute force or summation method. And as noted in red bold text, it's very, very slow. Now if you use it compute the discrete Fourier transform using the fast Fourier transform or FFT algorithm, that's very fast. And so there's another form of a discrete Fourier transform that I use in my little toolbox of discrete or digital signal processing toolbox is a DFT with FFT, and that's what's shown as the second example there, where the function name is DFT underscore FFT, and you pass it the same arguments. You pass it the sequence X you're trying to look at and the size of the DFT you want it to compute. And that is much faster. That FFT version of computing the discrete Fourier transforms is much faster by an order that we talked about in part 1 of the presentation of n times the natural log of n, where again n is the size of the sequence that for which you're computing the discrete Fourier transform. And I'll show a brief example here of how you might, if you were given a discrete Fourier transform, a discrete filter coefficients, and you wanted to verify in advance before you started actually implementing the filter that you understood what the coefficients represented, and then you get the expected magnitude and phase or frequency response of the filter before you actually implement it. So let's assume, for an example, you were given there's a filter, a notch and a low-pass filter that someone wanted you to implement, and they provided you the coefficients as individual filters themselves. So you got a low-pass filter, so you got the coefficients A sub L and B sub L is defined there, and that's just the numerator-denominator polynomial of that low-pass discrete filter. Then you're given polynomials A sub n and B sub n, which again are just the numerator and denominator polynomials of a notch filter. And then you're told, okay, this filter should be operated at 50 hertz. So you define the sample frequency fs 50, and the update interval t is 1 over 50, or 0.02 seconds. Then how we would go about computing the impulse response of this is again, we define an impulse. In this case, we want to make a 4,096 point impulse response. So we predefine an array called impulse to be all zeros with a length of 4,096. And then after computing it all zeros, we set the first element to 1. So that's going to give us an impulse response function where a value of 0 is the first index, and all other values or indices have a value of 0. Then we're going to individually pass this impulse response into the recursive filter using the numerator and denominator polynomials for first the notch filter and then the low-pass filter. So you see the two calls to recursive filter there towards the bottom of the figure. Xn then would be the impulse response of the notch filter. XL then would be the impulse response of the low-pass filter, each individually implemented, not together. And then you individually compute the discrete Fourier transform of the notch impulse response and the low-pass impulse response as shown there using, again, the FFT version of the discrete Fourier transform function. And notice, again, in this implementation, I'm doing them separately. So, we treat the filter as two individual stages, the low-pass stage and the notch stage, and then we'll look at the composite effect of the two combined together. So now once we've computed the magnitude and phase of the notch and then the low-pass filter, we can combine the magnitude and phase by just adding them. Since the magnitude is typically provided in dB, you can then add them, which is the equivalent of multiplying the two together if they were absolute magnitude and not dB. And of course the phase, you just add them together. So now mag and phase, as defined at the bottom of the figure, are the total magnitude and phase of the combined notch and low-pass filter. Now we'll look at the Batty plot of that frequency response. So what we have here is on the top magnitude in dB versus frequency, and phase in degrees versus frequency. And note again that we've said many times here, this particular plot has been converted back to real frequency. The frequency that would come out of the DFT, or discrete Fourier transform, is going to be normalized frequency, which would range from 0 to 0.5. And so if you want to convert it back to real frequency that maybe you can understand a little better, you would multiply that normalized frequency by the sample frequency. In this case, it was 50 hertz. Now, several things I want to point out here. What I've shown here is three separate lines. There's a red line, which is the notch filter only, the blue line, which is a low-pass filter only, and the black line, which is both filters combined together. And you'll notice if you look at the magnitude of the red line on the top plot, you see it does have a steep notch down around 2 hertz, and then it returns back, and above 3 or 4 hertz or so, it's back to 0 dB attenuation. So in other words, it's a very narrow range where it attenuates a signal. The low pass, on the other hand, has very low attenuation at low frequencies, and as you pass through 2 hertz, it starts rolling off per its characteristics. Two things I want to note, though, is the center of the notch, you notice, is approximately at 2 hertz. It's not exactly. It's actually 1.95 hertz is the smallest, the minimum attenuation you get, and that attenuation is about minus 26 dB. And if you continue that line on over to where the composite, or both, the effects of both filters are seen, it also attenuates at 10 hertz and above approximately 26 dB, or at least 26 dB as you go higher frequencies than 10 hertz. One other thing I want to note on the bottom figure that will be important in a couple of slides here to follow for this example is note the phase lag at 1 hertz due to the combined filters. You'll see that at 1 hertz the phase is approximately minus 65.7 degrees of phase lag at 1 hertz, and that'll be important for part of the example I'm going to show in a couple slides here. Now that we've looked at that, and like I said, the exercise, the reason you did that was you wanted to verify that you understood how the discrete filter coefficients were provided to you, and before you go to the next step of implementing them in some flight controller or whatever, you want to make sure you understand them right. So that you would go do the previous step that we showed on the previous couple slides, and convince yourself that you do understand what you've gotten and there's been no mistakes made. Now you want to say, okay, I'll show an example. All right, how would you use this to do something? The reason you define a notch low-pass filter is to try to filter out some undesirable characteristics for some, might be a sensor, and you want to notch out some noise that's present, or you might have your flight controller might be very sensitive to signals at certain frequencies that you want to notch out. So I'll show how you would actually implement such a filter. Now, notice from the construction of this filter that we identified from the frequency response on the previous page that the notch is centered at 2 Hertz, where at that frequency it has at least 26 dB of attenuation. And also the low-pass attenuation, the part that attenuates higher frequencies, has at least 26 dB of attenuation for frequencies at 10 Hertz and above. So knowing that, I'm going to build a specific sinusoidal waveform that will pass through that filter and see what we get out. So we'll define a 2048 point test waveform that's going to have 3 sinusoid components. We'll build an amplitude 2 sinusoid at 1 Hertz, and that'll be a normalized frequency of 0.02 for a filter operating at 50 Hertz. In other words, 1 Hertz over 50 Hertz is 0.02. So that'll be the normalized frequency for that component. We'll define another component which has an amplitude of 4 at a sinusoid of 2 Hertz. And again, that'll be a normalized frequency of 0.04. And that'll be, since it's at 2 Hertz, it's right at the center of the notch filter. And that first 1 Hertz signal is below the notch filter as well as below the low-pass roll-off. Finally, we'll add a third component which has an amplitude of 1 at the 10 Hertz sinusoid. And again, that 10 Hertz would be a normalized frequency of 0.02. And that should be above the low-pass filter's cutoff, so it should start to see attenuation due to it being a higher frequency term beyond what the low-pass would pass through unattenuated. So then shown below is a MATLAB or Octave command you could use to build a 2048 point sample of those 3 sinusoids as described. Now, what should we see before we actually go through this process? Let's think about what we would expect the filter to do. That high frequency component, the one at 10 Hertz or a 0.2 normalized frequency, we should see an attenuation of at least 26 dB. Or that comes out to be a 0.05 amplitude compared to the original signal. The component within the notch, that 2 Hertz component that we built in the signal, should also be attenuated by approximately 26 dB, which we saw from the frequency response of the filter itself 2 slides ago. Then finally, the low frequency component, the one at 1 Hertz, should pass through with little or no attenuation, but with some phase lag. And as you might remember from slide 2 slides ago, I encourage you to remember the phase lag at 1 Hertz was 65.7 degrees, and we'll show why that is important here in a moment. So what the steps we would do then is we want to compute the 2048 point impulse response of the discrete filter by convolving the input signal with the total filter's impulse response, or so-called the filter kernel. And the steps required to do that are basically 3 steps here. So these will be like MATLAB commands that you might use to do this. And the two functions we're going to use is one we've talked about before, is recursive filter. And that's just an implementation of a recursive filter where you pass it the thing you want it to filter, and then pass it the numerator, denominator polynomials of that filter, and then it will, in effect, implement that filter. Those are not built-in MATLAB functions. They're just MATLABs I've built for my own purposes. Then finally, there's a convolution that uses FFT, and that's what's shown at the bottom of the slide. The function name is convolve_FFT, and that just basically implements convolution but using FFTs. Because again, as we've mentioned before, convolution is very, very slow if you just do it the brute force method, the summation, where you sum the terms together, because you're doing order of n calculations. And so with a 2048 point sequence that we're going to be convolving here, that would be like 2048 squared, or a lot of calculations. So the FFT form of the convolution is very much faster than what you would get if you just did the so-called brute force method. So another thing, couple things to notice here is we've got a 2-stage filter. You know, it was provided presumably as a separate filter, discrete filter for a notch, and a separate discrete filter for a low pass. So how would you put them together? Here's one example, and I'll show you another example at the end of this presentation. That's probably how it will be done in the real world flight controls. But in this example, we take the impulse response and pass it through the notch filter first. So we retrieve the output of that and just call it filter notch, and it's recursive filter impulse response using the coefficients of the notch filter. Then we take that output called filter notch and we pass it into the recursive filter, now with the coefficients for the low pass filter, and the output of that we'll call filter notch low pass. So And then we will take the input signal that we're trying to condition. In other words, the sinusoid, or the sequence that we built, described on the previous slide, that consisted of those three sinusoids. That was saved in an array called X. So now we'll do a convolution of that signal, X, with the impulse response of the notch and low-pass filter. And that's what the output of that I've called X filtered. And again, this is one way you can implement filters. You would actually, in the real world, use a recursive filter just like I did on the first two steps. But this just shows an alternate way to do it, and I'll explain in the closing chart here as to another way you would do it that would probably be more like it would be implemented in the real world. So now what we get when we do this process as described on the previous slide, the figure to the right here on the top shows in red the original unfiltered signal. So that was the sinusoid, or the sequence that we built, that consisted of three separate sinusoids, one at 1 hertz, one at 2 hertz, and one at 10 hertz. And you can see the nature of it. It has obviously several sinusoids kind of combined together. Then the blue line on that top slide, or top figure, is the result of that filtered calculation on the previous page, where basically we had performed the convolution of the unfiltered signal in red there with the impulse response of the combined notch and low-pass filter. And sure enough, you see it's cleaned it up significantly. And we'll show a PSD and some other information on a couple of next slides to show that in a little bit more detail. But first I want to go back and touch on something we talked about before. Now for just this one discussion here, I'm going to go back and I've rebuilt the signal X sub n, where now it contains only the 0.02 normalized frequency component. That is only the 1 hertz data. So just as for talking purposes or illustration purposes, I'm going to rebuild X and go back and repeat the steps that were shown on the previous slide. So now what you should see is, and what you see at the bottom right of the figure here, is the red line is the signal X sub n, where it contains only the 1 hertz signal. It doesn't contain the component at 2 hertz or the component at 10 hertz. And the blue line, again, is the filtered result of that. When we go through the steps we did on the previous page to run that through our notch low-pass filter. And what you see there is it shows the magnitude has not been attenuated at all appreciably. You look at the magnitude of the two red line and the blue line, they're basically the same, still plus or minus 2, which is what the input was for that 1 hertz signal. You do see some phase lag between the two signals, so there's a time shift in the results. If you look very carefully, you can actually compute that phase lag as 9 samples of the data, where again we're sampling at 50 hertz or 50 samples per second. And you can compute the predicted phase lag, and we mentioned earlier that from the frequency response that we showed when we first verified our discrete filter, that we understood what was in it, it had a phase lag at 1 hertz of about 67.5 degrees. Well, you can show very clearly with the little equation I showed there that 65.7 degrees of phase lag at 50 samples per second corresponds to 9 samples of lag. And that's exactly what you see there. I didn't show it on this particular slide, but if you take that filtered signal blue and just introduce a time lag of 9 samples, you can slide it back over and it lines perfectly up with the red line, just as expected. So what that showed, the reason I emphasized that was that showed that at the low frequency part of the domain, the 1 hertz, the notch low pass filter didn't touch the signal except for introducing some phase lag. So it passed through that amplitude untouched, and the higher frequencies did get attenuated, as you see in the upper plot here, and we'll discuss that a little bit more on the next 2 slides as well. So now we'll go back and use the techniques that were defined in part 3 of this presentation and compute up the power spectral density, or PSD, of that input signal, X sub n, the original signal, and we'll also compute the PSD of the signal that's been filtered by the notch low-pass filter. So again, the red line on the figure on the right is the PSD of the unfiltered signal. The blue line, keeping with convention on the previous page, is the PSD of the filtered signal. And a couple things to note right away is note the original signal in red shows 3 distinct peaks there, one at 1 hertz, one at 2 hertz, and one at 10 hertz. And it should, because we built the signal with those individual 3 sinusoids in there. Note also, just for information, notice the relative magnitudes of those peaks of the PSDs in the red. you'll notice the 1 over 10 hertz is a magnitude of about 0.8, and the units here are, it's units squared per hertz, recall from PSD. So it's about 0.8 units squared per hertz. The component at 2 hertz, or excuse me, a component at 1 hertz is about, call it 3.5 units squared per hertz, and the component at 2 hertz is about 13.5 or so units squared per hertz. And if you looked at the magnitude of the original input signal, the component at 1 hertz had a value of 2, the component at 2 hertz had a value of 4, and the component at 10 hertz had a value of 1. And since the PSD is units squared per hertz, the ratios ought to be, the component at 2 hertz ought to be about 4 times as big as it is at 1 hertz, which is what you see there, and the component at 10 hertz ought to be about 1/4 what it is at 1 hertz, which it is as well. So that also shows you, it reiterates kind of one more time or reinforces what was presented in part 3 of this presentation about PSDs. You can actually use them to investigate where frequencies might be embedded in a signal, as well as get some insight as to what the relative magnitude of each of those components is. And that can be useful if you're taking lab data for some device, like be it a sensor or whatever, and you want to build a notch or low-pass filter to try to attenuate signals at certain frequency regimes that are not desirable in your flight controller. Then finally, you want to notice that the filtered signal, the PSD for the filtered signal in blue, doesn't show any content except at 1 hertz, and that's by what we desired. We built the filter, or excuse me, built the sequence so that the notch low-pass filter that we have been given would attenuate the higher frequencies and the content within the notch, but not attenuate the low-pass or the lower frequencies, and that's exactly what we see here. One other thing I'll do with this, just to reiterate or emphasize once again what's going on here, is we'll take the 2 signals here, the unfiltered and the filtered, and we'll compute a 1024 point DFT of the signals themselves. So we'll compute the DFT of the unfiltered signal X sub n. We'll compute a DFT of the X sub n that's been filtered by the notch low-pass filters, and we'll plot what's shown on the right there is just the magnitude versus frequency. So it's the Batty plot, but I've just skipped the phase here because the magnitude is what I want to emphasize. And what you'll notice is at low frequencies, over to the left of the figure, there's very little attenuation in the magnitude. And again, that's a log scale on the bottom. So 10 to the 0 that you see over towards the left, the first little peak there is 1 hertz. And the second peak you see over to the far right is 10 to the 1, or 10 hertz. So for low frequencies, 1 hertz, or they're slightly over 1 hertz to less than 1 hertz, you get basically the 2 magnitudes for the filtered and unfiltered signals lie right on top of one another. So that's reinforcing, again, you got very little or no attenuation at the low frequencies, which is what you expected given this was a low pass and notch filter. Now notice the second peak there that occurs at 2 hertz. You don't see a scaling for that because of the log scaling used, but you'll note that it's a very sharp attenuation there, which is what by nature a notch filter does. And if you look at the peak of the blue line and the red line there at 2 hertz, there's approximately 26 dB of attenuation. In other words, the blue line is about 26 dB smaller than the red line, where each of those divisions, you see there are 10 dB per small minor division on the vertical axis. Correspondingly, over there at 10 hertz, again, if you look at the peak of the red line at 10 hertz and the peak of the blue line, you can see approximately 26 dB of attenuation there as well. And also notice as you go from 2 hertz to 10 and beyond, there's a region where it's just gradually, the attenuation is increasing, and that's what we saw from the Batty plot of the notch low pass. It's got a real tight band of attenuation right around the notch, and then as you get farther and farther into the roll-off of the low pass filter, then it starts attenuating continually or gradually more and more and more as you go to higher frequencies, and that's what you see here. Now I want to offer a few comments here on the previous example before we conclude this section of the presentation. The previous example, we implemented the filter as the convolution of the input signal itself, X sub n, with the impulse response of the filter. And the impulse response of the filter is also what's known as the filter kernel. And we also used, as I described a couple of slides ago, we used the FFT version of the convolution operation because it's extremely much faster than just the so-called brute force or summation method. And also recall way all the way back to part 1 of this presentation that convolution can be implemented as the inverse discrete Fourier transform of the product of the discrete Fourier transform of each input signal. And so what that is, we go back to the equation that I used back in part 1 of this presentation. We'll show that if the little f with a curly bracket around there shown in the center of the page represents a Fourier transform. So if we have two signals, two time domain signals, f and g, and we want to, if we compute our f and g, and then also the asterisk operator here is going to denote convolution, not multiplication. So f star g is the convolution of the time domain signal f with the time domain signal g. If we take the Fourier transform of that convolution of f and g, that's equivalent to the product of the Fourier transform of f times the Fourier transform of g. So then, writing that another way, the time domain convolution of f of t and g of t can be equated from the inverse Fourier transform of the product of the Fourier transform of f times the product of the Fourier transform of g. So the main question is, why would you go all that much trouble? Why don't you just do the convolution in the first place? Well, again, the answer is it's much, much faster to do discrete Fourier transforms using an FFT algorithm than it is to just do the convolution by brute force method, or just by its definition as a summation. And also, the final thing I want to point out here, which I touched on a moment ago, is you can also implement the discrete filter directly as a recursive filter. Instead of convolving the signal to be conditioned, x of n in this case, with the filter kernel or impulse response of the filter. So you can do it by convolution, but in general, the way you'd really do it in a flight controller is you'd build a recursive filter, and that's what I'm going to show here in this final example. Now we'll implement the previous examples notch low-pass filter using just recursive filter calls. You might recall from the previous example that we implemented the filter as the convolution of the signal to be processed with the impulse response function, or so-called filter kernel, of the combined notch low-pass filter. In practice, that's probably not the way it would be implemented in a flight control system as a filter, but instead it would be done with recursive filters. And there's two examples I'll show here how it can be done also. Recall that we have in our example the notch and low pass parts of the filters are provided as separate discrete filters. So the low pass filter consists of a numerator polynomial AL and a denominator polynomial BL, and the notch filter is represented by a numerator polynomial AN and a denominator polynomial BN. So the first example I'll show here, we'll just do two successive calls to a recursive filter function, first passing it the signal x to be conditioned through the low-pass part of the filter, then passing that filtered result through the notch filter. The result of those two steps would be the combined notch low-pass filtering of the original signal. So the first example shown there is to call to the recursive filter with the first input being the signal to be conditioned x. The second and third inputs are the numerator and denominator polynomial coefficients of the filter. So we'll pass x into the recursive filter with AL and BL as the numerator denominator polynomials of the low-pass recursive filter. The output of that step we'll call x underscore low. Then the second step is to take that filtered value x underscore low, which is implemented the low-pass filter, and filter that again, now providing the recursive filter the numerator denominator polynomials of the notch filter. That's AN and BN. So then that second output we'll call x underscore filtered. So now after completing those two steps, x underscore filtered is the same signal as what we presented in the previous example that was created by performing the convolution of x, the original signal to be filtered, with the impulse response function of that combined notch low-pass filter. Now another way to do it, or yet another third way to do it, is to instead of independently running the signal to be implemented through two successive calls to the recursive filter, in practice you would probably just combine the notch and low-pass filter's numerator-denominator polynomials into a single numerator-denominator polynomial consisting of the combined notch and low-pass filter. In fact, that's probably how you would be given the filter definition in the first place. If the person who created the filter would just have combined them together and given you one set of numerator denominators that represents that entire filter. But if you were given separate filters, here's an example how you would build a multi-stage filter from individual filter elements. So the first example there is we'll take the low-pass filter numerator AL and the notch filter numerator AN. We will convolve those using the built-in MATLAB convolution function CONV, and then the output of that process step will be called A. So A now represents the numerator polynomials of the combined notch low-pass filter. And recall from part 1 of this presentation where I described that one of the features of convolution that can be used is for it to multiply two polynomials together term by term. So in addition to the normal or other uses of convolution that we have demonstrated in digital signal processing, it's also very useful just to multiply two polynomials. Now we'll do the same thing with the denominator, but there's a couple of extra steps involved that I'll describe in a moment. You'll notice the first step below for computing the combined notch low-pass filters denominator is I can convolve two temporary arrays that I've built here. The first one is has an element 1 as the first index and minus BL, the coefficients of the low-pass filter, as the ensuing elements. The second temporary array has a leading coefficient of 1 and minus Bn as the remaining coefficients in that array. Then the convolution of those two temporary arrays I'll store in an array called B. Following that convolution, I negate B and extract only elements 2 through the end of the array. In other words, I eliminate that first element. Then I can implement that combined notch low-pass filter with just a single recursive filter call now. So the step where we see x underscore filtered equals the call to the recursive filter with the first input being the signal to be conditioned, and then A and B being the numerator and denominator polynomials of that combined notch low-pass filter. So that shows that you can implement that multi-stage discrete filter as a single call to a recursive filter. And that's probably how it would, as I said, would be done in the real world. Now, just a couple of comments of why those extra steps were required to create the denominator polynomial for that combined discrete filter when we didn't have to do that for the numerator. And the answer is, recall from the discussion earlier of recursive filters that discrete filters generally have an implied leading coefficient of 1, and the coefficients in the denominator also are assumed to have a minus sign associated with them. You might recall the form of the denominator polynomial for the standard form of discrete filters is 1 minus b1 z to the minus 1 minus b2 z to the minus 2 minus b3 z to the minus 3, etc. So the coefficients in the denominator are like 1 minus b1 minus b2 minus b3, etc. And again, since the leading coefficient is always a 1, that's normally not even provided. You're not even given that. So the actual denominator polynomials for both the notch and low-pass filter are, in actuality, 1 minus bn, that represents the entire coefficients for the notch denominator. 1 minus bl actually represents the polynomial coefficients for the low-pass filter. So that's why we had to add the leading coefficient of 1 and negate the remaining coefficients before we perform the convolution. And then again, after we're performing the convolution, again you need to eliminate the leading coefficient of 1 since it's assumed, and then negate the remaining coefficients. Well, this will conclude part 4 of this 4-part discussion of digital signal processing. And this slide I'll attempt to summarize what we've covered in all 4 parts. There's a lot of material here, so we'll briefly recap what we've provided. In part 1, which was entitled Mathematical Concepts, we laid the framework for the discussions that we had in the ensuing 3 parts. We discussed the mathematical definitions of Fourier transforms and the convolution operator, what discrete Fourier transforms mean and what the mathematical basis of those is, and what FFTs or fast Fourier transforms, how they are nothing more than just efficient ways to compute the discrete Fourier transforms. We also discussed in Part 1, towards the end, the Shannon sampling theorem and data aliasing and the effects the sample frequency has on the data that you retrieve when you're computing samples of some continuous time waveform. In Part 2, which was entitled Power Spectral Density Basics, we covered primarily the definition of power spectral density, or PSD, and how it's used to estimate the spectral characteristics of waveforms. And we discussed also some of the tools that are provided as part of normal PSD products to allow you to enhance the spectral characteristics and kind of get rid of some issues that make it difficult to interpret what you have. And that was followed up by a PSD demonstration where we built a function that had several sinusoids, a constant bias term, and a random component, and we used the PSD to show how we could retrieve the contents of the signal and extract where the particular sinusoids were located. We also did that in this presentation a few slides ago, as you might recall. In Part 3 of the presentation, which was entitled Implementing Discrete Filters, we covered the following, basically how you would implement filters in the continuous domain, as well as how you would implement them in the discrete, or Z domain. First of all, we started that discussion by discussing Laplace transforms and Z transforms and how those can be related using Tustin's rule of the bilinear transformation to transform from the S operator of the Laplace domain to the Z operator of the Z domain. And then that's key to converting continuous domain filters into discrete filters. We also showed how you can build a recursive filter that actually implements those discrete filters, which we've then used in this part as in an example that we just covered. Finally, in this last part, Part 4 of this 4-part series, which has been entitled Typical GNC Applications, we covered the following. We discussed normalized frequency, what that means, and how that's related to the topics we had discussed in the first 3 parts of the presentation. We also identified methods, or showed methods you can use to evaluate or verify the transfer function that you get for a particular discrete filter. And as I said, I strongly encourage you, whenever you're operating with discrete filters, to do that step and commit yourself via the magnitude and phase that the filter it represents what you think it represents, and then you go ahead and implement it in your controller or analysis tool or whatever you're using it for. And then finally, we concluded this last part with an example how you might use such a filter to implement a notch low-pass filter, and then some of the characteristics you get out of it and what the benefit of it is. So I hope that you found this presentation to be useful and informative, and I invite you to continue with the other presentations that are available from the NESC Academy Online. Thank you.